Hi everyone, thanks for having me today. I wanted to thank specifically Damien and Paul, for their warm welcome and for recruiting me back in New York, and inviting me to a nice place to convince me to come. That was nice. So today I'm going to talk about AI at scale at Twitter. So as you can see, I put a lot of ads because I have to, right? That's part of the brand. Also, ranking the timeline. So I hesitated, like, should I put the S at the end of this title? I wasn't sure. Am I ranking one timeline? Is it the concept of ranking the timeline? Am I ranking all the timelines in the world? Anyway, I'm going to focus today on how do we rank the timelines on Twitter. So for those who don't know, the main way people use Twitter is via the timelines, right? So it's some kind of a news feed where you see tweets scrolling down, right? And so we are ranking these timelines now since not that long ago. So I'm going to talk about that, go in details, and try to extrapolate from that to see why it's important to have good tools to build machine learning and how we can build a machine learning platform. And ultimately, maybe, what is the future of machine learning platforms? So yeah, this is the agenda for today. First introduction, I'm going to tell you more about the team, about, well, not myself, that's not very interesting, but just the team. Then number two, I'm going to describe to you what timelines ranking means very quickly. What is the scale of the problem, right? Because that's one important thing. Then after that, I'm going to tell you about the work we did to introduce deep learning in timelines ranking, which is not an obvious thing because we have a lot of constraints that need to be respected. Then number four, I'm going to talk more about the machine learning platform. The goal is to improve productivity of machine learning engineers. So how do we do that? What are the key concepts to improve the productivity of machine learning engineers in a company like Twitter? And then finally, I'm going to briefly mention, if I have time, what the future of AI platforms could look like in tech companies and at Twitter specifically. So, intro. Yeah, so I am the head of Twitter Cortex. I am in New York. The team is split between New York and San Francisco. We are in charge of building the machine learning platform for Twitter. So the way it happens was not so smooth, It's not like we were like, oh, we're going to build a team that's going to build a machine learning platform at Twitter. Didn't happen that way, right? So when we joined, we were acquired by Twitter in 2014. So the acquisition was a small one. We were just the 5 of us, starting from a company called MadBits. So a very small startup acquired by Twitter. But at the beginning, we focused a lot on image and media classification and understanding. So we started doing stuff like, hey, we can recognize porn in images, so you don't have to. I mean, that's one of the first things we did. That's interesting. So you can see the date. It's like a year later, but we did some other stuff as well. Don't worry, Then we founded Twitter Cortex, which was this team with a nice name, similar to Google Brain. It was that time of the hype where every team doing AI had to have a cool name. So we said, wow, Twitter Cortex looks good. What you see here, the mosaic here, is pretty interesting. That's something we showed a lot of times. And the upper part of this mosaic is only images of porn, and the lower part is like random images. Of course, you can see it. I'm not going to zoom in, but that's pretty funny to see that it's difficult to distinguish, right? So kind of summarize AI at scale, Then after that, we acquired another startup at Twitter, which is called WetLab. I don't know, like maybe some of you are aware of that fact, with very strong research capability. Then we did something else. We kept focusing on video, and we started trying to understand real-time live video content. So I'm sure a lot of you know about Periscope. Periscope is a live streaming app that belongs to Twitter, right? That was acquired by Twitter. And so we were able to, in real time, understand that using GPU clusters for inference of data, so related to the talk before. So that was a big move. Helped us like recommend better live streams for people and blah, 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 and so on. And also filter out bad content. Then there was another acquisition, a big one this time. We acquired a company called Magic Pony. Yeah, the name is pretty cool too. That acquisition was so cool that we also had an article in French, Mais que fait Magic Pony, So we had this article. That was great. A lot of good press, blah blah. So these people are extremely good, and what they're working on is very advanced. They're doing a lot of work on super resolution, so how to reconstruct noisy images and make them look good, right? So this is very related also to media compression. So how do you compress media in a good way so that you can optimize for network bandwidth and that kind of stuff, right? Yeah, they're very advanced. They have great researchers, and they publish quite a lot of paper. Yeah, so, but the thing is, we focused a lot on media for a long period of time, but then we realized that a lot of teams at Twitter, along with the commoditization of AI, right, needed our help to actually do machine learning, right? So, you know, engineers, normal engineers, right, not ML experts, needed to actually use machine learning to introduce it in their products. So product could be, for example, ranking the timeline. It could be recommend tweets via notifications, for example, any kind of trying to tackle abuse on the platform and that kind of stuff. So we decided to change the story of the team, the charter of the team, and to say, okay, now we're going to focus on building a machine learning platform for Twitter, and so make everybody else very efficient. And the first prototype of that work is kind of summarized here in a very abstract and difficult to understand way. I just show it because it's cool to see that we are using a trendy type of AI, you know. Trendy type of AI means deep learning here, just so you know. But basically what we do here is we use deep learning to rank the timelines for Twitter. Before that, we used other technologies, right? So decision trees and that kind of stuff. Now we switch to using deep learning. So I'm going to focus more on that specific thing. So first, what is timelines ranking? Very brief overview. So on Twitter, the timelines used to be reverse chronological. So you had the most recent tweets first. But the thing is, let's say you're following 2,000 people, then your timelines becomes a nightmare, right? So like you have, I don't know, so many tweets, so much noise. So a lot of people were actually leaving the platform because of that, right? There was also a lot of tweets that were just like not interesting, side by side with tweets that people are actually really interested about. So we try to say, okay, how can we be more relevant? How can we make sure that you only get the best tweets for you, right? Given your interest, given the people you follow, and given the content of the tweet as well. But maybe also the time of the day and blah, blah, blah. So we need more relevance. One solution to do that is to rank the tweets according to a relevance score, right? So that's the first approach. And so this is great. Like this is what Twitter settled on. We're going to rank the tweets. We're going to assign a score for each of these tweets, and we're going to show it to you in that order. So the thing is now we have to build it, right? So that took a lot of time. So I'm just going to give you an idea of the scale of the problem in numbers. So on Twitter, we have billions of user engagements per day. So user engagements is something like liking a tweet, retweeting a tweet, you know, even clicking on a tweet is an engagement. So this is what we use to train the model, right? So like, for example, we can learn to predict the probability that you're going to like a given tweet, okay? So this is the base of the model. And so you can imagine the amount of training data we have, right? Compared to, for example, data sets like ImageNet, which I'm sure a lot of you are familiar with, which is kind of the standard data set for images. ImageNet is a bit more, like 1.2 million, I think. So that's for the kind of the standard one. You have the bigger ImageNet, which is maybe like 10 million or something like that. But in that case, we have every day, we have billions of positive user engagements. Positive, so meaning the negative side is even bigger than that, you know. Because of course, like we would like people to engage more, but sometimes they just scroll and don't like the tweet, right? So this is a lot of training data. Another thing that's very, very, very important and took us a lot of time to actually circumvent, I mean, make work with deep learning was we have 6 million tweets to score per second at peak. So every time you go on Twitter and you go on the timelines page, basically there is a request that's being sent, right? That says, okay, well, can you give me the best tweet? So what it does is it's going to query like a bunch of candidates very quickly. Then it's going to rank them using a very light model. And then it's going to send that to a bigger model that's more advanced to re-rank it again. And then it's going to serve it to you. So you can imagine all the machinery to first generate these candidate tweets, then rank them the first time, send them, rank them again, and then send them again to you, right? And then visualize them and so on. All of this 6 million times per second, right? And also, one other big constraint we have is the total time budget to do all of this is 1 second. So if we do more than 1 second, the process is interrupted, you get your reverse chronological timeline. So that's pretty intense, right? Like we have to make it work under those constraints. And if we don't respect that, there is no way we can even deploy deep learning in production in the timelines. So yeah, in terms of impact, that's pretty impressive because since we started ranking the timeline, we got 4.5 million DAU. DAUs are daily active users. 500 million UAF, it's user active minutes on the platform. A lot more engagement, so like 140 million favorites, 35 million retweets, blah, blah, blah. More tweets composed, actually. That's interesting. So like people reply to tweets they like, for example. And more spending on ads, which is also a good thing, right? Because we're a company and we try to make money, so. And all of this, so it shows that ranking the timeline is actually useful, right? All right, so the data, very important because compared to, like, for example, image classification problems, we are not dealing with images, and actually we are not even dealing with like huge computation or convolution and stuff. I mean, we can talk about that more. It's a lot of sparse features. So what is a sparse feature? It's, let's say, as this user interacted with the producer of this tweet, for example, ever before. That's a sparse features because most of the time it's going to be 0, like no, right? So let's say as soon as you reach more than 90% of time where it's 0, you can maybe call it a sparse feature. Anyway, this is a problem that, and we have a lot of data, right? So this is a problem that deep learning research that does not really approach, right? And so we had to find our own solutions for that. So how did we do that, right? I'm gonna chat quickly about that. So what we had to focus on, of course, was speed to make sure we were in the latency budget, right? That's the first thing. Better ranking, because if we are not able to do better than the previous algorithms, then what's the point? And then fast training, because since we have billions of data points, we need to be able to train in a reasonable amount of time, especially since we want people to be able to experiment quickly every time they want to improve their models, right? So when they add features, blah, blah, blah. So we had to improve these 3 things. How did we do that? In terms of speed, we implemented custom code on CPU and even GPU. So GPU is not really very well adapted to sparse computation, but GPU is still good because it has a high memory bandwidth, higher than like classic hierarchical CPU architectures. So it's interesting. Yeah, it's good for us to implement custom code on GPU for that reason. What I'm saying here is that the bottleneck for sparse computation is not the computation on the CPU itself, on the processor. It's a memory bandwidth, right? Getting the data from memory and writing back. So we are trying to, we're working on that, and we get, for example, back in the days, I think TensorFlow improved on that, but we get like 2 to 4x speed up versus TensorFlow just on sparse matrix multiplication. Sounds stupid, but we had to do it, so we did that. Then better ranking. Well, that was not easy. You can think that deep learning is going to be better than decision trees plus logistic regression. Well, actually, it's not that simple, right? So we had to do a lot of work there to improve. One big problem we had, for example, is how to say, the click-through rate, I would say, yeah. So the percentage of likes on average, right? So the average is like something, it's very low, right? I don't know, less than 1%. And the percentage of replies, for example, is even lower, right? It's like maybe 1 in 1,000. If you train a deep net, so a deep net is a highly non-convex problem, right? Deep learning is a highly non-convex problem. So when you try to solve it, I mean, there are no rules that guarantee you that you're going to converge to the right solution. So you have to do a lot of tricks. One of these tricks is to sample the data kind of equally between positives and negatives. That's great. So let's say we do that. But if you do that and you learn a model on that, then your model is going to predict the probability at the same, the average sampling ratio is going to be the average probability you predict. So this is not what we want because we want to predict the exact probability. So we added a module that's called isotonic calibration. Anyway, that gives you, in the end, an actual probability calibrated on the real distribution. We also added some max normalization and other custom modules, and we get much better results than before. But without those, we were not able, just by throwing a deep net directly, we were not able to get better results than decision trees. So there was a lot of work put into that. Then fast training. Well, Very quickly, for sparse problems, one good thing to do is to run Hogwire. So basically, we train in parallel, multi-threading on the same parameters, and we update the parameters in a very noisy fashion. So each thread updates parameter, and the OS is responsible for writing that to the parameters in memory. And that's not very theoretically very sound, right? But it works very well and allow us to like scale linearly with the number of threads, which is a good thing. Of course, then we implemented some sophisticated HDFS streamer and so on and so forth. So yeah, that was a lot of work, and we managed to get excellent results with that. This improved again like ad spending and so on, as we could see before. Now the thing is, this was great, but now we want people to be able to reproduce that prototype all the time. How do we do that? Like, we want people to be productive, use deep learning in their daily job. So when I say people, I'm talking about machine learning engineers at Twitter. So who are the machine learning engineers at Twitter? We have multiple kind of machine learning engineers or machine learning experts, right? So some of them are not even experts actually, right? But we have different types. One would be what I call the pure research type. So just so you know, like all these types are overlapping, right? There's no clear boundary, and like if you do research, you only have to do research. But pure research, typically these people do a lot of model exploration. They do not sample new data sets. They do not really like fiddle with data, right? Usually they try to explore new model architecture to solve a problem. So they need a lot of flexibility. So for example, they need frameworks like PyTorch, to do their research. That's why they love PyTorch so much in general. Then applied research, so that's slightly different. In general, the people doing applied research are also exploring model architecture. But one thing is they're trying to solve an actual practical problem, right, for the company. So what they're going to do is they're going to have to fiddle a lot with data to build a data set, like a clean data set. For example, let's say you want to do word2vec on Twitter tweets, on Twitter words. You need to be able to sample data that's clean, right? If you don't have clean data, then your word embeddings are not going to be good, blah blah blah. So there's a lot of work to do there. So they need flexibility and robustness. And then there is the production workflow, which is really like people who don't touch the model architecture, but they do a lot of feature engineering. So they want more input, more informative input to their model, and retrain easily, and have maybe automated testing and that kind of stuff, right? So we focused on the last one to start with, but we want to extend the platform to all of these types of workflows. So the ultimate goal is to increase the number of experiments per machine learning expert. So to do that, we invest in like 3 different categories. One is automation and visualization. It's like how to build workflows that can automatically retrain your models, for example, automatically test your models. Visualization is all about, okay, you want to store your results whenever you do an experiment, visualize them via a nice UI, and so on and so forth. We also want to provide a friendly AI environment, so something that's highly performant, that can run on different types of hardware, but it's very easy to use, right? And where also people can use techniques that are different, such as decision trees, but also deep learning, but also blah, 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 right? So that's the second thing we invest in. And finally, one part that's pretty hard is to actually integrate with an infrastructure that first was there before and is optimized for distributed systems, right? So very large distributed systems is not optimized for machine learning from the get-go. So being nicely integrated with that and maybe influencing the infrastructure to actually integrate machine learning is one of our goals as well. Yeah, so I have 21 seconds. So I'm going to talk very quickly about the future of AI platform. That's just what I think personally. So you see that diagram is typically the kind of stuff that happens. You see model A, B, and C. Model A, B, and C are typically models that run on the right path. So when you send a tweet, that tweet is like classified, for example, or like we generate an embedding out of this tweet, or any kind of information that's a smart representation of your tweet, for example, right? Could be images, could be any kind of a client event, could be transformed by these models. Then the thing is, usually we want to store this to databases, right? To make them available later as features to product models. So when you rank the timeline, you want to be able to have access to this smart representation when you serve the timeline. So it needs to be stored, then used by the final model D, and final model D actually ranks your timeline, makes recommendations, and so on. So basically, yeah, to do that, what would be great, is to be able to do this in a very managed way, where we can easily deploy one part of the graph on the write path, one part of the computational graph on the read path, with intermediary database abstractions that make it very easy. So right now, this is very tied to the infrastructure. So it's very difficult to propose an open source solution for that kind of things. The tendency right now, the trend is to do this in cloud. So I know Google, like Google Cloud, GCP is trying to push for this a lot. They are not there yet, but like they're probably the closest. We are trying to do the same with Twitter infrastructure at the moment. But this is what we are trying to focus on: offline and online consistency, integrated with infrastructure, and managed deployment. Thank you.